Non, c'est la prochaine musique.
Okay, audio test, 1, 2, 1, 2, 1, 2.
So we're about to start again. So our next speaker is Conrad Beddington, and he's going to talk about audio standards, and we first start with AES67, a transport protocol for audio.
Okay. So, hi, I'm Conrad Beddington. I'm here from Focusrite. We make audio interfaces and various other kinds of audio equipment. And yeah, I'm talking about AES67, a standard for networking in pro audio industry. So, just to set the scene, what we're looking at, the industry itself is studio audio, live sound, also things like broadcast, and also theatres, house worship, all those kinds of things that have sound systems and audio handling. So traditionally audio's been done over analog, there's been a move to digital, and more recently there's been a move to networked audio. So the type of devices we're looking at here range from microphones, preamplifiers, so getting your audio in, mixers and effects to process your audio, interfaces to connect it up to different things, all the way out to amplifiers and speakers, so you can actually hear it. So here's, just for example, a typical live sound setup. This is the kind of thing we have. So we have microphone inputs here, and various sound sources which get fed into the audio network. This will be taken via the Ethernet over to a mixing console, perhaps to a computer, so you can record. And the audio is processed here, and then sent back out over the network to our output system, which will be for monitoring on the stage and for front of house sound, so the audience can hear it. So that's a pretty typical setup. So in an audio network, we have specific requirements. We're only dealing with local area networks. We're not putting audio over the internet. And that frees us up from a lot of variability with traffic levels and congestion. We want low latency we want high quality, and most importantly, we want lots of channels, and we cannot have lossy compression in these systems. We want good, pure quality audio. So the existing technologies, there's already stuff serving this market, and there are various kind of proprietary technologies. So they're just various brands there, and we can have a look at them in some detail. So there's various levels of protocol and various solutions within those levels for all of our different proprietary audio technologies. And as you can see on this chart, there's a lot of proprietary stuff in these systems. So that actually hurts our interop. Us, you know, connecting these audio systems together is actually quite difficult. So that's both a limitation that impacts convenience. It impacts future-proofing, which can be quite an issue. A lot of this equipment is expensive, so so being able to knowing that you can use it in the future is quite important. And there's a particular pain point in the broadcast industry, especially with a lot of live sound in studio. You can just be careful what you buy and put into your system and have it be compatible. With broadcast, they want to go to other people's events. They want to take their OB truck, their outside broadcast truck, take it to the stadium. This is from Wimbledon, and they want to plug into the audio systems and the video systems on that stadium and get feeds of what's going on so they can broadcast. So we can't deal with bad interop here. So AES67 is a standard developed by the Audio Engineering Society, aiming to bridge these technologies together. It specifies various levels of the system, but it specifically excludes device discovery and control because that's not so necessary for transporting the audio between systems. And it was seen as better to get some level of standardization rather than devolving into kind of a big discussion that goes nowhere. So those areas were excluded. The technologies in AES67 are actually all fairly standard existing IT technologies. In the audio industry, it's a relatively small group of companies compared to, say, your Googles or your Amazons or whatever. So they don't necessarily have huge amounts of engineers to put at the problem. So anywhere they can reuse an existing technology is a benefit. So yeah, this is AES67 just bridging the various technologies on IP, and here's an overview of what's in it. So at the very bottom layer, we have our audio format. We just use PCM, nothing fancy there. We use RTP packetization. We use a precision time protocol, that's an IEEE standard. And then for session description and connection management, we actually borrow from kind of the voice over IP world, and we use STB and SIP. So yeah, so I'm going to just take through each layer now. And at the bottom layer is the audio format. We standardized on linear PCM. There are two formats that are mandated by the standard. Those are the 48 kilohertz sample frequency formats. And then the optional formats, the lowest quality is CD quality, the higher quality is 96 kilohertz 24-bit. And the standard leaves it open that you can implement other formats, but these are the standard ones. So once we've got our audio, we put it into packets. We use RTP for this, and for simplicity, the AES67 standard actually specifies that you cannot use CSRC, so you can't use contributing sources, and you can't use header extensions. A lot of the audio processing happens on embedded hardware devices, so keeping things simple is important here. The standard mandates 8 channels per stream and has short packet times. That's the amount of audio time-wise you put in a packet. So that's short to keep the latency down, and yeah, multicast is optional. Now, in order to make an audio network work, there's synchronization. This is kind of the magic thing which differentiates an audio network from a typical media setting. In a typical setting, there is some tolerance for things like a sample glitch or a slight delay or those kinds of things, and some jitter buffers. In an audio network, there is less tolerance for this. A sample glitch being amplified up on a massive sound system is quite harsh on the ears, shall we say. So to do this, we use an IEEE standard, the 1588. This uses a consensus selection system to select a master clock. And then periodically, between kind of 4 times a second and 10 times a second, the master clock initiates synchronization with all the slave devices. And over a time period, those clocks converge. And once we have this network clock, as it's called, we derive a media clock by a simple multiplication. So in a typical case, running at 48 kilohertz sample frequency, it's just defined that 1 second of network clock has 48,000 sample times in it, and that's just simple multiplication. So the synchronization process is done in 2 stages. First is the clock sync, where the master sends a sync packet and then notifies the receiving slave of what timestamp that had. Once that's done, the slave can initiate a delay request where it goes, I think the time is this, that goes back to the master. The master measures what the time is, and it sends back what its time was. And using this, we can measure the network delay, and after a few cycles, the clocks will converge because we will know our network delay, we will know where our master is, and we can converge our clocks. It typically takes a couple of seconds for a clock to converge in most situations. So once we've got our audio, we've packetized it, and we've synchronized, we need a way to tell our different devices what our actual audio streams are, and this is where session description comes in. We mostly use the SDP standard. There are a couple of additional header items, are they called header attributes, sorry, in our SDP. These specify what packet time we're using and what our clock sources are and how to map payloads. The rest of it is standard SDP, so if you've seen an SDP before, yeah, it looks something like this. So in this case, we're sending 8 channels of audio at 48 kilohertz. There's a 250 microsecond packet time, so we're sending quite short bursts of audio quite often. That keeps latency down. And here we specify a precision time protocol clock domain, which is our synchronization mechanism. And then we just offset the media clock from that time domain. So now to connect things together, we have the connection management. This is SIP, again, a very standard protocol used widely in video conferencing, voice over IP, various other industries. It's based on URIs. And in AES67, the standard recommends actually using serverless mode. So SIP allows you to put a lot of infrastructure in your network for transforming SIP requests, routing them to places, and that's kind of not recommended for this use case. It overcomplicates things. So in AES67, serverless mode is used, and you just have direct connections between your audio devices. So a simple SIP session, this is as simple as it gets, is device A just invites. If device B can receive the media, device B just says, yep, okay. Media flows, and then to tear the connection down, there's a bye packet and an okay. That's the simplest case, and if you look up SIP, you can see there's various, lot more complicated cases available. The other connection management we have is IGMP. This is for multicast. So it's possible to have a network device put out the audio onto the network to a multicast feed. And in this case, we just use the standard IGMP, which tells the network routers where this audio is required. There's no direct connection between the sending device and the receiving device. As far as it's concerned, it's just putting audio onto the network, and whatever needs it will just pick it up. And so that simplifies our stack, and it has all the usual advantages, bandwidth, usage, whatever, etc. So that's what's in the standard. So who's the organizations? Well, there's 2 of them. There's the AES, the Audio Engineers Society. They're handling the standardization and the technical discussion around the standard. And then there's the Media Networking Alliance, who are more involved in the actual promotion of the standard and some of the more informal discussion around what should go in and how to do it. So there are a number of members of the Media Networking Alliance. There's Focusrite there, there's Yamaha, there's Harman, there's Bosch Security, and there's also associate members. These tend to be less equipment manufacturers and more like actual media companies. So, for example, I believe Swedish Radio is an associate member, as is the BBC, and I think Walt Disney Imagineering, that those kinds of companies are all associate members. So the things I want to get across here are the AES67 is standardization, and that improves interop. It's bridging a gap that was previously couldn't connect devices together. It shows the reuse of general purpose technology in a specific environment, in this case for audio. And it's also showing kind of the growing interaction between the technology industry and the pro audio industry. Previously there's some interaction, but with the growth of audio networks, there's a lot more in networking in general, and there's a lot more overlap now. So for more information, there's the Media Networking Alliance, and you can go to the AES for actual copies of the standards documents. They're pretty long and deep, and as you expect from those. So I think that's it for now. Thank you.
Okay, so we've got plenty of time to take questions on AES67. We have the first question there.
Okay, FOSDEM.
Yeah.
The open source developers make it very good code. I've been searching it for 2 months. In fact, all I could find is a GitHub account with a stub. But this could be a driver for Linux. And also AES has not number of AES, but $50 to get a spec. You download it, and it's not open. I don't have the right to distribute it. So even if I pay $50, I can't develop a driver with it. So no point is driver. So how do you see the future of an open source driver? Because Ordinate with predominance actor in the patent pool, which lies behind in Europe. So far patents are not allowed, but these are of course hardware native. So there's a patent pool with it. And Ordinate ships a driver for Linux for a standard NIC networking interface.
Yeah.
Standard, a good one, maybe Intel 210, something like that. And you can have it for free as in freebie as long as you buy some hardware kit. But the driver is there, and it doesn't need some hardware. Is there some advice in that front?
Okay, so the question roughly is around there is certainly lacking open source code for this standard, and there is a certain amount of dominance around Ordinate and their patents. So I'd say that in terms of opening up, having the standard is kind of probably the first step. And I admit that there is a long way to go with interaction between, say, pro audio and the open source community. So I view having standard as a first step on quite a long path.
While the standards might not be free, or not for money, it's basically just a collection of other open standards. You can find them with the IETF, IEEE, etc. It's nothing special, more a collection of different standards.
Yeah, and it's a grade. You have to know how to make the recite.
And for open source implementations in Ustream we support it, except for the connection management. That's something the application will have to do.
And it's supported by what?
We supported in Ustream by the code that we have.
You should have to repeat what he said.
Okay.
Okay.
So if you want to look at that,
Yeah.
Okay, so that's a point that the AES67 is mostly supported in GStreamer. Did you say that the connection management isn't?
Sorry?
Did you say connection management isn't?
Everything except for connection.
Okay, so all the standard except for the connection management is now supported in GStreamer. Thank you. I didn't actually know that.
Did you have a question, Sebastian?
No.
Right.
So I also would like to add, in the same as GStreamer, AES67, apart from connection management, is supported in UPipe. But anyway, the main part of that is, so when we implemented it, we just implemented it, I think either from a draft or just from the underlying documents. We never paid $50 because we try and avoid, where possible, paying taxes to the standard.
Yeah.
The standards industrial complex, as I like to call it. So, good that he's not listening. Good. The main question is, so we have a lot of problems with trying to interact even with professional manufacturers of sound equipment on Linux in the main.
Yeah.
So for example, clocking is an issue that we have, although you're talking about PTP, there's lots of applications where there's not PTP and typically not AES67. But do you have anything to suggest to the kernel people about how they can make ALSA in particular more suitable towards a professional use, because it's a struggle?
Okay, so this is a question around sound development in Linux and how we might make ALSA better for the professional case. Yeah. Oh, that's a tough one.
Because to implement AES67 properly,
yeah.
You need real support in ALSA.
Yeah, you need real support.
Well, it doesn't exist. So.
This is a tough one because personally, being in audio more, I haven't been on Linux all that much recently. I don't know really. Yeah, that's quite deep. ALSA's quite deep into the drivers and like those areas, and I'm not so sure about.
Perhaps if you have a video later, Kieran can discuss.
Yeah.
Other questions? Well, thank you, Conrad. We return in 5 minutes for AES70.
Okay. Yeah, sure. Oh, yeah.
It's just easier That's a useless clock. I need X clock, not some very jittery clock. When I need to connect to different things, maybe in some small scale
No.